To make sure that you understand how to apply the things we just covered up to now in section 5, you'll find a detailed example in the lecture notes that you can see here as well. This example is about Sirius, which is a star that you can see here. You're given some properties. Specifically, its apparent R band magnitude and B band magnitude, and also what is the parallax angle of Sirius. It's a very standard problem of the things that you'll be able to do from now onwards with very limited information. So 2 magnitudes and 1 parallax angle. And with the tools that we already covered, we'll be able to determine the distance from the Earth, the B absolute magnitude, MB, the surface temperature of the star, and the expected peak wavelength. How do you do that? We can start with number 1, which is the distance from the Earth to Sirius. This is very easy. We covered this in section 2. The only thing you have to do, because you already have a parallax angle, is to do 1 over the parallax angle in arcsecond, and you get the distance in parsec. For part 2, you're asked to calculate the B absolute magnitude of Sirius. What you do is to plug in the ingredients. You can start just by writing the equation for an absolute magnitude in terms of distance, or you could write it in terms of a parallax angle. Because we have a distance, I've just used that. If you plug in the values, you find out that the absolute B band magnitude of Sirius is 1.38. To estimate the surface temperature of Sirius, we're not really given any peak wavelength, so we can't use Wien's law, but we've covered how we can use colors to actually estimate temperatures. This is an example of how you can apply the empirical formula that I derived. So the first thing you would do is to calculate the B minus R color. This is just a difference of magnitudes you're given in the question. This will be minus 1.1. Remember, because this is lower than 0, you would say that Sirius is blue. It's actually very blue. And if you plug in into the equation, you'd find out that Sirius is actually quite hot. It's almost 10,000 Kelvin. Because we've determined the temperature, we can actually use Wien's law to predict what should be the peak if you were to take a spectrum of Sirius. And it turns out to be 292 nanometers. And this is well into the ultraviolet. So our eyes would actually not be sensitive to most of the light coming from Sirius. And on top of that, we've also seen in this section that in the ultraviolet, the atmosphere is quite opaque, so we wouldn't be able to see that either. The final things that you now know how to do is, for example, to determine Sirius's luminosity in solar units in CGS, and also the radius of Sirius in solar units and in kilometers. And we've seen just before how in solar units, you can very easily calculate the luminosity of a star if you know its absolute magnitude. In this case, we're comparing the one that we did for B bands. And if you do it, you realize that Sirius is actually quite bright. It's 24 times the solar luminosity. And converting to CGS is relatively straightforward. Finally, to determine the radius of a star, such as Sirius, in solar units, the easiest thing is to use this expression, which we've seen how to obtain. And ultimately, you'd find out that Sirius is larger than the sun, about almost 1.7 solar radius. And finally, to convert to kilometers, you just need to know how much the solar radius is, and then convert it to kilometers, which would be 1.15 times 10 to the 6 kilometers.